Welcome to the Deep Dive. Today we're tackling a subject that's likely crossed your mind. The methods and research involved in gaining unauthorized access to a high-security server.
Uh-huh.
For you, someone who appreciates getting to the heart of complex topics efficiently, think of this as a guided tour through the tactics and thinking used in network security attacks.
Okay.
We've compiled a set of fascinating sources detailing practical demonstrations and code-level explorations of these methodologies.
Right.
Our goal is to extract the core insights for you in a structured way, providing clarity without getting lost in, excessive technical jargon. Okay, let's dive in.
What's fascinating right away, I think, is that when we consider breaking into a heavily fortified digital vault, the approaches aren't always the direct explosive breaches you might imagine.
Right, not like the movies.
Exactly. Our sources highlight a more calculated landscape where attackers often probe for weaknesses, sometimes using what seem like minor disruptions as a way to test offenses or, create openings.
So less brute force, more finesse.
Yeah, it's less a Hollywood-style instantaneous hack and more a step-by-step process of reconnaissance and exploitation.
Okay, and our sources actually start by looking at denial of service attacks. Now, you might initially dismiss these as just annoyances, right?
Yeah.
Things that temporarily knock a website offline.
Sure, that's the common perception.
But, as we'll see, they can be a significant part of a larger attack strategy. Picture this. You're trying to use an online banking portal that's like you at the ATM.
Uh-huh.
Now imagine someone floods the login page with fake requests, making the server totally overwhelmed and unable to process legitimate logins. You, the actual user, are locked out.
Right.
That's the essence of a DOS attack.
Yeah.
Overloading a system to prevent authorized access.
That banking portal analogy really hits the nail on the head. Our materials describe three main outcomes of a DOS attack. First, the server might simply get bogged down, just too busy handling the flood of malicious traffic to respond to genuine requests.
Just spinning wheels.
Exactly. Second, in more critical scenarios, the server might crash altogether or become totally unresponsive, needing a reboot.
Ouch.
And third, even if the server soldiers on, legitimate users will experience significant delays and much slower response times. Think about waiting the normal, fraction of a second for a web page versus staring at a spinner for 5-10 seconds, maybe even longer.
Yeah, that kind of delay effectively makes the service unusable for you.
Totally.
And it's a bit of a surprise to learn, isn't it, that even with all the advanced cyber defenses out there, our sources remind us that these foundational DOS attacks still pose a threat.
Yeah, particularly to systems that haven't received the latest security updates or applications that have known weaknesses.
Right. Our sources also delve into distributed denial of service, or DDoS attacks. This takes our banking portal scenario and just, amplifies it massively. Instead of one person causing trouble, you have a multitude of compromised computers, all simultaneously bombarding the target.
Precisely. The sources point out two primary types of DDoS attacks. One is often associated with hacker groups or, hacktivists. They might rally their members to use readily available tools. Names like LOIC, Sapphira, HULK, and XOIC are mentioned.
So like a digital flash mob.
Kind of, yeah. It's like a coordinated digital protest where participants download these tools and aim them at a specific target. The other, potentially more concerning, is botnet-driven. This involves vast networks of infected computers, the bots controlled remotely by an attacker through a command and control center, or CCC.
Ah, the CCC.
Yeah, these botnets can be enormous and generate truly overwhelming levels of malicious traffic.
Okay, so DOS and DDoS attacks can create disruption, maybe act as a smokescreen. Now let's get into some specific techniques our sources highlight. First up, we have the intriguing billion laughs attack, also known as an XML bomb. Okay, let's unpack this. What's the core vulnerability being exploited here?
The billion laughs attack takes advantage of how XML documents can define entities. Think of them as custom shortcuts for longer pieces of text or code.
Okay, shortcuts.
The attack works by creating multiple nested layers of these entities. Imagine Russian nesting dolls, but instead of just a few, you have many, and each one expands dramatically in size.
Oh, wow.
So a tiny initial piece of data can just explode into a massive payload.
Right, and the source gives a really clear illustration using these entity variables like lol, lol1, lol2, and so on, up to lol9. Each level multiplies the size by a factor of 10, so by the time you reach lol9, you're dealing with a colossal amount of data, hence the billion laughs.
Exactly.
For someone who doesn't code, the actual XML payload might look like, a jumble, but the source explains it follows a top-down structure. defining these expanding shortcuts step by step.
Yeah.
So how do you protect against this kind of exponential data explosion?
Well, the sources point to a couple of key defense mechanisms. One is restricting document type definitions, or DTDs. Think of a DTD as the rulebook for an XML document, specifying what elements and those shortcuts the entities are allowed.
Okay, limiting the rulebook.
Right. By limiting what can be defined in this rulebook, you limit the attacker's ability to create these nested data bombs. The other is reducing entity substitutions, which controls how many times an entity can be expanded.
That makes sense. Now, there's a variation on this called the quadratic blow-up attack, another flavor of XML bomb. How does this one differ in its approach?
Unlike the billion laughs attack, which uses many layers of nested shortcuts, the quadratic blow-up attack uses a single shortcut, a single entity that contains a very, very long string of characters.
Just one long string.
Yeah, and this one long shortcut is then called repeatedly throughout the XML document. The key difference is that the size of the resulting data is directly related to how many times this long string is called. The more repetitions, the larger and more damaging the effect.
So less nesting, more repetition.
Exactly. It's less about exponential growth through nesting and more about multiplied impact through repetition.
The source even gives us a glimpse into a practical demonstration, mentioning specific IP addresses 192.168.174 as the attacker and 192.168.161 as the target in one instance. It really grounds the theory in a real-world scenario.
Yeah, seeing the IPs makes it concrete.
And it sounds like the defenses we just discussed for billion laughs, those restrictions on DTDs and entity substitutions, would also be effective against this quadratic attack.
Absolutely, because both attacks fundamentally exploit the same mechanism within XML, the way entities are expanded. Those core mitigations address the underlying vulnerability.
Yeah, okay. Our sources also briefly mention an XML RPC DOS attack. What's the basic idea behind that one?
The source material touches on this as essentially another method to launch a denial-of-service attack against a web address, a URL that is publicly accessible.
Right.
Imagine a server that accepts specific types of messages to perform actions remotely. An attacker can craft a flood of these messages, or maybe very resource-intensive ones, to overwhelm the server's ability to process legitimate requests.
So same goal, different message type?
Pretty much. The core aim, like other DOS attacks, is to disrupt access to the service.
Okay, moving on to a technique that sounds almost contradictory. The slow HTTP attack, also known as a low-rate DOS attack. How can being slow cause so much trouble?
It's actually pretty clever, a subversion of typical attack methods. Standard DOS attacks try to overwhelm a server with sheer volume, a massive surge of requests.
Right, the flood.
The slow HTTP attack takes the opposite tack. Instead of sending a flood of complete requests, the attacker sends incomplete HTTP requests, but does so very, very slowly.
Trickling them in.
Exactly. The server, anticipating the rest of the data to arrive, keeps the connection open and allocates resources to it. If an attacker can establish and maintain a large number of these languishing, incomplete connections, they can gradually exhaust all of the server's available resources.
So it ties everything up.
Preventing it from responding to legitimate users like you.
Yeah.
Resource exhaustion, essentially.
The source mentions tools like a Python script or slow tpitus on Kali Linux being used to carry out these attacks. It also describes the test setup with an attacker at 192.168.168, targeting a WordPress site at 192.168.194 with a monitoring machine at 192.168.0.138. Again, seeing these specific IP addresses really illustrates how these attacks can be simulated and studied.
Definitely helps visualize it.
And what kind of defenses can a server employ against these slow, persistent attacks?
Well, the source highlights the use of the request timeout module. This allows a server to set limits on how long it will wait for a complete request.
That's a time limit.
Right. If the client doesn't send the remaining data within that set time frame, the server can proactively close the connection and free up those resources. Implementing robust security controls, like, intrusion detection and prevention systems, can also help identify patterns indicative of these low and slow attacks and block the originating traffic.
Makes sense. Next up, we have the SSL renegotiation attack. Now, SSL is the technology that's supposed to secure our online connections, so how can it be turned into an attack vector?
Yeah, it's a bit of a security paradox. Secure Sockets Layer, SSL, and its newer version, Transport Layer Security, TLS, use a process called a handshake to establish a secure, encrypted communication channel.
The handshake, right?
This handshake involves complex cryptographic calculations that can be quite demanding on the server's processing power. The SSL renegotiation attack exploits a feature that allows a client to request a new handshake, a renegotiation even after a secure connection has already been established.
Wait, why would you need to do that?
There are some niche use cases, but it turned out to be exploitable. By repeatedly forcing the server to perform these resource-intensive renegotiations, even from a single compromised machine, an attacker can drain the server's CPU capacity.
Yeah, CPU exhaustion this time.
Exactly, ultimately leading to a denial of service for everyone else.
The source mentions using the OpenSSL's client command to initiate this type of attack and Wireshark, a network analysis tool, to actually observe the renegotiation process in detail.
Lets you see it happening.
It sounds like identifying servers that haven't implemented defenses against this is crucial for an attacker. What kind of defenses are effective here?
Well, the source emphasizes the importance of identifying and applying security patches to vulnerable servers, as always. But a significant defense mechanism is the ability to disable TLS renegotiation altogether in certain configurations.
Just turn it off.
Yeah, if you don't need it. For example, TLS version 1.3, the most recent one, was actually designed to prevent client-initiated renegotiation in the same way, making systems using it immune to this specific attack.
Good to know. Okay, we've covered a range of fascinating techniques, many focused on disrupting access by overwhelming resources or exploiting specific protocol features. Now, our sources also delve into the world of botnets and their role in launching attacks. We touched on this earlier with DDoS, but let's explore the mechanics.
Right, the botnets.
You described botnets as networks of compromised computers controlled by an attacker's command and control center, the CCC. These bots are essentially obedient, if unwitting, soldiers in a digital army. How are these armies assembled in the first place?
The sources outline several common infection methods. One is by embedding malicious software or malware on compromised websites.
Drive-by downloads.
Exactly. Unsuspecting users visit these sites, and the malware is silently downloaded and installed, turning their computer into a bot that then connects back to the attacker's CCC. Another prevalent method is through phishing emails.
Classic phishing.
Yep. These emails often contain malicious attachments or deceptive links that, when clicked, install the bot software. Exploiting software vulnerabilities, security flaws in operating systems or applications is another significant avenue.
Unpatched systems again.
Right. If a system has a known weakness, attackers can exploit it to gain access and install their bot. Even seemingly innocuous fake tech support scams can be a vector.
Really? Tech support scams?
Yeah, attackers trick users into granting them remote access to their computers, which they then use to install bots. Finally, in some instances, attackers might control large groups of servers that they can directly commandeer as a source of bots.
Wow, it sounds like a really pervasive and frankly difficult problem to combat. The sources even provide some insights into the underlying code for both the NetBot's CCC server and the individual client bot. Starting with the CCC server, what are some of its key operational components?
Okay, the server code, as described, is fundamentally designed to listen for incoming connections from infected machines. It's typically configured to listen on all available network interfaces, that's the 0.0.0.0 you often see, and a specific communication port.
Waiting for the bots to call home.
Exactly. Its core function is to maintain a real-time inventory of all the bots that are currently online and responsive. When a new bot connects, the server uses a function called accept to establish that connection. Now, to manage potentially thousands of bots simultaneously, the server employs a technique called multi-threading, using a threaded function to create a separate process for each connected bot.
So it can talk to many bots at once.
Precisely. There's also a received function that handles any data sent back from the bots to the server, and a function named configure, which is likely used for initial setup and configuration of the bots.
And issuing commands.
Right. The server code also includes support for different types of attacks, with flood and ping specifically mentioned as examples of attack commands it can issue. And interestingly, there's a for-country function mentioned, which suggests the capability to target attacks based on the geographical location of the bots.
Targeted attacks. And on the client side, what does the code for a typical NetBot look like? How does it know where to connect and what to do?
The client bot's primary task is simple. Establish a connection with the CCC server. The server's IP address and the designated communication port are crucial pieces of information that are hard-coded or configured within the bot software.
Gotta know who the boss is.
Exactly. Once it successfully connects, the bot typically sends a heartbeat message back to the server, a digital "I'm online and ready" signal. It then enters a continuous loop, just constantly listening for commands from the server.
Waiting for orders.
Yep. Based on the commands it receives again, examples like flood and ping are mentioned. The bot executes the corresponding attack against the specified target. The client code relies on standard programming libraries like socket for network communication, time for managing delays, threading for concurrent operations, OS and subprocess for interacting with the OS, request for web stuff, and signal for handling system signals.
So a toolkit for causing trouble.
Basically. The sources also point out the role of status codes like launch, halt, hold, and update in allowing the server to precisely control the bot's actions and the ongoing attacks.
So the CCC acts as the central nervous system, issuing commands, and the bots are the distributed agents carrying out those commands. It really illustrates the power and, well, the potential scale of these malicious networks.
Yeah.
Now, we've spent a lot of time discussing the various attack methods. What strategies do our sources suggest for defense and mitigation overall?
Well, throughout our conversation, we've touched on specific countermeasures for individual attacks, things like restricting DTDs and entity substitutions for those XML bomb attacks,
Right, the XML stuff?
using request timeout to defend against slow HTTP attacks, and disabling SSL renegotiation to prevent that type of DOS.
Uh-huh.
However, the sources also emphasize broader security principles that are, absolutely essential. This includes the fundamental practice of regularly patching operating systems and applications to address known security vulnerabilities.
Patch.
Always. Implementing secure coding practices during software development and rigorously validating all user input can also prevent many types of attacks right from the start.
Building security in.
Exactly. And finally, deploying web application firewalls, or WAFs, can provide a critical layer of defense by examining incoming web traffic and blocking known malicious patterns and attack attempts before they even reach the server.
So, multiple layers of defense.
You need them.
So to recap, our deep dive today has provided a fascinating, if somewhat sobering, look into the techniques used to gain unauthorized access to servers, focusing primarily on the realm of denial of service attacks.
Yeah, mostly DOS and related techniques.
We've seen how attackers can employ tactics ranging from simple brute force flooding to more intricate exploits of XML parsing, and even the very protocols designed to secure our communications. We've also examined the architecture and operational principles behind botnets, highlighting their capacity for large-scale coordinated attacks. For you, the listener, we hope this has illuminated the underlying mechanisms and provided some valuable insights into this critical area of cybersecurity.
Indeed. And if we step back and look at the bigger picture, understanding these offensive techniques is absolutely crucial for building effective defensive strategies. It's a continuous cycle, really, an arms race.
It really is.
Attackers constantly seeking new vulnerabilities, and defenders working tirelessly to close those gaps.
On that note, here's a final thought for you to consider. In an increasingly interconnected world, where so much of our lives and critical infrastructure relies on digital systems, what are the broader implications of these attack methods? And, what does it mean for the ongoing efforts to protect our digital landscape?
Yeah, big questions.
It's a complex and constantly evolving field, and one that certainly warrants further exploration. Thanks for joining us on this deep dive.